Bond strength and bond length. The strength of a bond can be thought of as the energy needed to break the bond. This is called the bond enthalpy. We will discuss enthalpy in more detail later. In the case of chlorine, Cl2, the bond enthalpy, represented by D, parentheses, Cl-Cl, close parentheses, is 242 kilojoules per mole. This table contains the average bond enthalpies for a number of common bonds. Bond enthalpies are always positive because they are defined as the energy needed to break a bond. That is, energy must be added, so the energy is positive. This is a slightly enlarged version of the table to make reading the table easier. Each type of bond for each pair of elements has a different bond energy. Compare, for example, the bond energy of a carbon-carbon single bond with that of a carbon-carbon double bond or a carbon-carbon triple bond. The more bonds there are between the two atoms, the higher the bond energy. In general, the higher the bond energy, the stronger the bond. We can use the average bond enthalpies to get an estimate of the energy of a reaction. Imagine that we first break every bond in the reactants, producing individual atoms, and then take the atoms and make the bonds in the new compounds. We would have had to add the energy of each of the bonds in the reactants to break them. Then we would have gotten back the energy of each bond in the products when we made the new bonds. So, in principle, the change in the energy, that is, the reaction energy or enthalpy, could be found by adding up the energies of the bonds in the reactants and subtracting the energies of the bonds in the products. Here's the mathematical expression for that. The one drawback of this process is that we need to know what the bonds are, or at least what bonds have changed. Let's look at the reaction between methane, CH4, and chlorine, Cl2, to make chloromethane, CH3Cl, and HCl. In this example, one carbon-hydrogen bond and one chlorine-chlorine bond are broken, one carbon-chlorine bond and one hydrogen-chlorine bond are formed. So the enthalpy of the reaction is the bond energy of the carbon-hydrogen bond plus the bond energy of the chlorine-chlorine bond minus the sum of the bond energy of the carbon-chlorine bond and the bond energy of the hydrogen-chlorine bond. Substituting the numbers we find in the table, we get 413 kilojoules plus 242 kilojoules minus 328 kilojoules plus 431 kilojoules, which reduces to minus 104 kilojoules. We also talk about bond length. This is the distance between the atoms in the covalent bond. Looking at the table, we see that the more bonds there are between the atoms, the shorter the bond is. So typically, the shorter a bond is, the stronger a bond is. We can expand this idea to resonance. Here's the ozone molecule with its bond angle and bond lengths. If you compare the bond lengths of the two bonds in ozone to the oxygen-oxygen single bond and oxygen-oxygen double bond lengths, you see that in ozone the length, 1.278 angstroms, is between the two values given in the table, 1.48 angstroms for the single bond and 1.21 angstroms for the double bond. This is in agreement with the idea that the actual structure of ozone is a combination of the two resonance structures and has a bond length between the single bond length and the double bond length. It is not an uncommon question on the AP test to compare the relative lengths of the bonds in several compounds with different degrees of resonance. There are two problems using bond energies on the problem sheet for this part of the lesson.